All right, folks, we are back on section 12.4, studying nonlinear latent variable models. So far in this chapter, we've been talking about linear and Gaussian latent variable models, which are very simple to work with. But now we're going to look at some extensions of these. And generally, this section is going to be kind of a bit light on the math. He doesn't go too deeply into these methods, but it's just good to know for what's out there. And in his new deep learning book, some of these topics actually get expanded into entire chapters. So you can kind of look there if you want to get more of the details and more of the modern updates. Okay, so let's get into it. In this video, we'll do a brief covering of ICA, independent component analysis, which is a very important technique, very useful technique, also kind of on a theoretical grounds, talking, it's one of the ones which it really is kind of truly a latent variable model in the sense that we're actually very interested in the latent variables, whereas with, for example, PCA, the latent variables are a bit ambiguous. We care more about the subspace. So it's very useful just from that perspective of settings where you actually care about what the latent variables are and what that looks like and when you can actually say something about them. So we'll just talk about it briefly, and there's a whole literature on this. I might even do a special video on this topic if I get around to it, but we'll just go through what he's got. Okay, so let's start. So let me make sure you guys can see. Okay. Cool. So he says, in this chapter, we have focused on the simplest class of models having continuous latent variables, namely those based on linear Gaussian distributions, right? So we had Gaussian priors, Gaussian likelihoods, and linear projections from the latent variables to the observations. As well as having great practical importance, these models are relatively easy to analyze, as we saw, and to fit to data, and can also be used as components in more complex models. But here we consider briefly some generalizations of this framework to models that are either nonlinear or non-Gaussian, or both. So we're going to be talking about at some point sections where the projections from the latent variables to the observations are nonlinear projections, where let's say, for example, the priors on the latent variables are going to be non-Gaussian, and sometimes both of those things together. So in fact, the issues of nonlinearity and non-Gaussianity are related because a general probability density can be obtained from a simple fixed reference density, such as a Gaussian, by making a nonlinear change of variables. Okay, so this goes back to change of variables formula, and there are things now, I don't know much about them, but like there's a technique called normalizing flows, which really exploits this, which we can learn about. I think it's in the new deep learning book, but it's a powerful technique. So talking about how these you can transform Gaussians into whatever distribution that you want. Okay, so let's get into the topic of today's video, which is going to be on independent component analysis. Okay. So we begin by considering models in which the observed variables are related linearly to the latent variables, but for which the latent distribution is non-Gaussian. Okay, so here we just got, let's say y is going to equal to, actually it's going to, I think it's called x. So x is equal to a times z, but maybe z is distributed according to, something, who knows what, and it's going to have some non-Gaussian distribution. We'll see why that's important. Okay. An important class of such models are known as independent component analysis, or ICA, arises when we consider a distribution over latent variables that factorizes so that you see the components are independent, the elements are independent. Notice that, yes, we'll see that we actually had this same property held when we were doing PCA and factor analysis as well, but we'll see that we need more than just this assumption. So it's not just independence that's important. We'll see that kind of non-Gaussianity is also going to be important. Okay, to understand the role of such models, consider a situation in which two people are talking at the same time. So this is kind of the cocktail party problem, or the source separation problem. This is kind of one of the classic motivations for it, in which two people are talking at the same time and record their voices using two microphones. If we ignore the effects such as time delay and echoes, then the signal received by the microphones at any point in time will be a linear combination of the amplitudes of the two voices. So all he's saying is, y of t is going to be a two-element vector. Let's actually just make it more explicit. So we'll say, y1 of t, y2 of t. You guys can see that is going to be some linear combination, a11 A12, A21, A22 of x1 of t, x2 of t. And this is going to be like the x1s and x2s in this case are going to be the conversations, people's voices, and y is going to be what you picked up in your microphone. So simple setup. The coefficients of this linear combination will be constant, so those are the a's, but we don't know them. And if we can infer their values from sample data, then we can invert the mixing process. So the idea is we want to get the x's from the y's. So if we can infer them, yeah, assuming it's non-singular, so assuming you can invert it, and thereby obtain two clean signals, each of which contains the voice of one person. This is an example of a problem called blind source separation. So you'll hear about this a lot, in which blind refers to the fact that we are given only the mixed data, and neither the original sources nor the mixing coefficients are observed. Right. So exactly. So we don't know. So it says neither the original sources. So obviously that if we had them, this wouldn't be a problem, or the a's. So we need to get x and the a's, and the question is, can we even do that? Now, this type of problem is sometimes addressed using the following approach, in which we ignore the temporal structure of the signals and treat the successive samples as IIDs. So this would be as if, as far as you're concerned, when you take this approach, the ordering of your sample doesn't matter. So you can imagine taking your audio signal and just permuting just shuffling around the time, the time bins, or the samples basically in time. As long as you do it the same way on the input and the output, these approaches are ignoring the temporal information, so they're just treating them as independent observations, and they would give you the same result. Now, whether that's a good result and whether you can ignore the temporal structure, that will depend on your actual problem, but sometimes you can, and it will simplify our analysis. So we consider a generative model, so let's highlight that, in which there are two latent variables corresponding to the unobserved speech signal amplitude. So that's, you guys can still see, that'll be like their x's. And there are two observed variables given by the signal values at the microphones, these are the y's. The latent variables have a joint distribution that factorizes, so we're going to assume they're independent because, yeah, the key thing in this situation is you have two conversations and you assume they're happening in different parts of the room, so they're independent. There's not going to be any correlation between them. And there are two, The latent variables have a joint distribution that factorizes as above, and the observed variables are given by a linear combination of latent variables. There's no need to include a noise distribution because the number of latent variables equals the number of observed variables. So remember, we had to, in the probabilistic PCA, we had to bring in a noise distribution, partly because, hey, that was a description, that was the nature of the problem. Like there's, we assumed the data was coming from some projection, from some two-dimensional surface plus some noise, but also it allowed us to give meaningful likelihoods to points that didn't lie exactly on in that two-dimensional projection. So, but he's saying, and that was a setting where we were doing kind of a low-dimensional projection, and so it would have been possible for if we didn't have a noise distribution, then some observation values we wouldn't be able to assign probabilities to. But here, because we're not doing a dimensionality reduction, dimensionality is the same. We don't necessarily need to introduce a noise distribution. You can if you want to. Maybe there's some, maybe for example the microphones have some noise on top of them. But in the simplest setting, you don't have to do that. Whereas in PCA you did have to do it in probabilistic PCA. And therefore the marginal distribution of Therefore the marginal distribution of the observed variables will not in general be singular, right? So the observed variables are simply deterministic linear combinations of the latent variables. Okay, so we're just going to assume that it's just, this A matrix gives us how one goes to the other, and there's no noise, and it's just fixed. So for a given input, there's exactly one output possible. Another way of putting that is, you say like, for example, the probability of y given x and a is just the delta. So at y minus ax, something like this. Okay, so you guys can see that? Terrific. Okay, given the data set of observations, the likelihood function for this model is a function of the coefficients in the linear combination. right? So it has to be. The log likelihood can be maximized using gradient-based optimization, giving rise to a particular version of independent component analysis. And you can look at some of the references later for what some of those rules look like, but you do it in this, the maximum likelihood way. Just take some, gradients of matrices, and you get the result. So it's nothing too fancy there. It says the success of this approach requires the latent variables have non-Gaussian distributions. So let's see what goes wrong if they are Gaussian. So to see this, recall that in probabilistic PCA and in factor analysis, the latent space distribution is given by zero mean isotropic Gaussian, right? So remember what we had? We had P of Z is equal to normal of Z, 0, I. The model therefore cannot distinguish between two different choices for the latent variables where these differ simply by a rotation in latent space, right? So, let's see what he means by that. So remember we had X given Z was going to equal to A of, sorry, it's actually going to call W if we want to keep with him, W of Z, and let's forget the additive noise for now. It's not going to matter for this argument. Okay, so now we say, well, what's the likelihood of our data? So we would say, well, the probability of X given these parameters? Well, it's going to be distributed normally with the expectation of X, obviously, and the covariance of X. And from this expression, we see this, because Z is zero mean, this is 0, and the covariance is WWT. Okay? Now, so that's all you have to go on. So now the question is, well, okay, you think now you've identified your Zs are, let's say, those conversations that you were trying to pick out. You're like, great, I've identified them. The problem is that what if we just did a rotation? So Z goes to, let's call this, we're going to make a new Z. Z prime is equal to R times Z. So we're going to just rotate the latents. And so what we will see is that, well, and let's see what, with our new latents, what it looks like. Well, it's still going to be, it's W, R, Z. You're like, oh, well, that's going to give, that looks like it's going to not match the data. But again, when it comes down to the likelihood, it's going to be, the mean is still the same, so okay. And the covariance, unfortunately, well, that's going to be WR, RT, WT. And that's going to go, so this is going to be WWT. So in both cases, these two things are exactly the same, right? So in terms of your likelihood function, they're exactly the same. So in terms of estimating W, they'll be exactly the same. So you can still get at W, but you can't, the latents you recover, which is what matters for ICA. You actually want to get the conversations. You don't want some rotation of the conversations, which will be some like garbled version. You can't recover those. And so that's, there won't be any kind of unique way of picking them out under these assumptions. So yeah, you might get lucky and somehow your optimization procedure gives you the unmixed ones, but that'll just be by chance. So that's why that's the problem here. So it doesn't matter so much for like estimating W. That was kind of the focus of PCA and probabilistic PCA, kind of finding these projections, the data that capture tons of variance, finding some aspect of this mixing matrix. But it does matter when you actually care about recovering the latents, and that's kind of the key point here. All right. So this can be verified directly by noting the marginal densities. This was this thing that we care about. And hence the likelihood function is unchanged if we make the transformation W to W times R, right? Because the WRs disappear, the R's disappear, and the resulting covariance is exactly the same. Because the matrix C given by 12.36 is itself invariant. So that was this WWT. Extending the model to allow more general Gaussian latent distribution does not change this conclusion because, as we have seen, such a model is equivalent to the zero mean isotropic Gaussian latent variable model. So the idea was if you add some, maybe you can make, you can change this covariance on Z. Well, you can actually absorb that into W, and end up with Z itself again being isotropic Gaussian, and you end up with the same problem. Okay, so what can we do? Okay, so let's see what he says next. So another way to see why Gaussian latent variable distribution in linear models is insufficient to find independent components is to note that the principal components represent a rotation of the coordinate system in data space, such as to diagonalize the covariance matrix. So that the data distribution in new coordinates is then uncorrelated. Okay, so that's all that means. Zero correlation is a necessary condition for independence. It is not, however, sufficient, right? It's only sufficient if the data is Gaussian. It's not, however, sufficient. In practice, a common choice for latent variable distribution is one of these guys, which kind of looks like it's actually, well, it's a bit harder to see. So it kind of looks like this. So it has kind of heavier tails than the Gaussian. Yeah, I'll come back to this point. Let's just kind of finish the section. It's important. A common choice for latent variable distribution is given by this, which has heavy tails compared to a Gaussian, reflecting the observation that many real-world distributions also exhibit this property. Okay. The original ICA model was based on the optimization of an objective function defined by information maximization. One advantage of a probabilistic latent variable formulation that helps to motivate and formulate generalizations of ICA. For example, there's independent factor analysis, where you add more bells and whistles to this, then you do like maximum likelihood to estimate the parameters with EM. Many other types of models have been considered, and there's a huge literature. Right. I think one interesting thing about ICA too, though, is kind of flipping it around, is that, like, all of this stuff that we did requires having a probabilistic model. But what if your model is incorrect? And it turns out with ICA, you can use other principles to actually get exactly the same answer. So in many real life situations, your model isn't going to be correct, and so the question always arises, like, how well am I going to do when my model doesn't match the data? And you have to find that out empirically. And it turns out that with ICA, it's kind of robust to some of those things. So for example, you can get the same answer by maximizing like the non-Gaussianity of the latents that you recover, the conversation you recover. You can do it, via information maximization. You can do it assuming there's kind of some probabilistic model, but you don't have to. So it's kind of a nice, in some sense, you can view it as not a bug, but a feature of ICA. Now going back to this point, again, I think this section, he could have done a lot more justice to it, because he spent a lot of time on probabilistic PCA, but like he does not spend time on like ICA, which is actually quite important. I would say arguably more important than probabilistic PCA in terms of applications. So let me see if I can explain to you why this matters. Okay, so the issue is this. So suppose when you have these heavy tail distributions. Okay, so let's say when you start with like the Gaussian distribution, everything's like quite like elliptical. But when you have these heavy tail distributions, well, we can just start with the latents. They kind of have, they'll often have these cross shapes due to this heavy tailed nature, and these are like the contour lines. And then let's say this was the conversations, and they're independent. So you have like this is, let's say this is Z1, Z2. These are two conversations happening independently, and if you look, this kind of heavy tailed nature means that the joint distribution, in the prior distribution, will have this kind of structure. Now let's say we want to look at what happens when you look at the microphone signal. So let's say we're gonna look at AZ. You guys can see all of this. So that's gonna maybe like rotate things a bit. So maybe we'll get this kind of like this kind of an X shape, and I'm going to ignore the mean offsets and things like that. Okay, so the problem is, now what you're interested in recovering, remember, with ICA, you're actually interested in going from this. This is your observation. This is x1, x2. You want to go from x1 and x2 back to these guys. So you actually want to like figure out these components. So what PCA is going to do is it's going to try to give you an answer that's uncorrelated. So the problem with that is when the uncorrelated version of this problem, even after let's just do it. You'll see the uncorrelated version of when you decorrelate this, you won't get the components back that you want necessarily. So let's look at one uncorrelated version of this. Well, you can uncorrelate things by just tilting them like that, right? I just rotated. right? And this is uncorrelated because you can see for every value of x1, for every value of z, or recovered z1, the two values of z2 are equally likely, and so their expectation will be 0. So this is uncorrelated. So it will tell you, well, this is your estimate, and this is your other estimate. But you can see that there's dependencies between. It's just that the linear dependency is 0, but there's clearly a nonlinear dependency, which means your components aren't actually independent, which is what you assume about those conversations. You want to get independent components, you've got an uncorrelated component, but that's not strong enough. And so the independent component analysis will actually find a transformation of these that will actually make them independent. And you can see that in this particular case, independence will actually mean finding, recovering a joint distribution that has this kind of perfectly aligned, axis-aligned distribution of the latents. And you can see why, if you, all of this stuff will kind of go out the window if your distribution is kind of very round. So that's kind of why, this is kind of why, PCA versus ICA is useful for these, when you're actually interested in extracting latent variables. PCA, just doing the decorrelation thing, it won't be enough. So you need to actually do something stronger. You need non-Gaussianity to get this kind of cross-shaped structure in the, or star-shaped more generally in the latent space, and then you need to go for independence to actually be able to extract that. So that's, give you a little bit of intuition of what that's about. I think it's definitely worth reading more about this. I'll try to make a post about this myself, going into some of these details, these points in more detail if I get around to it. But I think it's worth looking at. I think he doesn't spend enough time on this section, I think, but it's a very interesting topic, and it really highlights, latent variable modeling, why we sometimes actually really care about latent variables in a very practically meaningful setting. So I think that's all I wanted to say about ICA. Hopefully that was useful. As always, just give me some comments if you agree, disagree, something wasn't clear, something was incorrect. Always happy to get that feedback. So hope you enjoyed the video, and I will see you in the next one where we will be talking about auto-associative neural networks. Talk to you then. Bye.